Right now, let's discuss the first in-term revised paper. Right, let's discuss with the first question. Right. So the question says, state whether the following statements are true or false on the dotted lines. Right. Okay, let's start with the question number 1. Right. So this is question number 1. What it says: rules related to polarization power. Rules related to polarizing power of cations and polarizability of anions predict that the melting point of KBr is higher than that of lithium iodide. Right? That was the question, right? So this is all about the ionic bond, right? We know about the ionic bond now. Ionic bond, right? Its strength is depending on the polarizing power of the cation and the polarizability of the anion, right? So what is the theory there? So if you take the cation, right? When its charge increases, when its charge increases, and when its radius decreases, its polarizing power increases, right? It comes to anion. When its charge increases as well as when its radius increases, its polarizability increases. When the polarizing power and the polarizability increases, what happens? Right? Your covalent character increases. That means your ionic character decreases. When the ionic character decreases, your melting points decrease. Melting points of your ionic compounds decrease, right? That is the idea. So when the polarizing power increases and the polarizability increases, melting points of your ionic compounds decrease, right? That is the idea. So let's copy the statement now. Proceed to polarizing power of the cation, okay. Polarizability of the anion, right? Up to there, the statement is okay. Predicts that the melting point of KBr is higher than that of lithium iodide, right? KBr and the lithium iodide, right? So when it comes to lithium, it's a small ion compared to the K plus, right? Lithium iodide, iodine is larger anion compared to small anion Br minus. So that is the idea. So let's compare. So charges are same. Charges are not going to be a fact here to differentiate the two guys with the melting points, right? So what happens? So what we need to discuss is all about the radii of these ions, right? So when the radius of the cation is smaller, so that is the smaller situation, right? Out of those two, the radius R plus is smaller with this one, and the radius of the anion is larger. The large radius is with this one, the size. When that happens, they are saying your melting points decrease. So with this one, the melting point is low. When the radius of the cation is small and the size of the anion is large, the melting points are low. That is what it says, right? So lithium iodide is with a lower melting point than KBr. That is what we can say. So we can say because melting points, right? The lithium iodide This is a smaller melting point than the KBr, right? See what it says. Melting point of KBr is higher than that of lithium iodide. Melting point of KBr is higher than that of lithium iodide. So the statement is true. So we can take the first statement as a true statement, right? It's a true statement, right? No, that is clear, right? Let's move to the statement number 2. Statement number 2, what it says: the electron gain energy of beryllium is positive. The electron gain energy of beryllium is positive. That is what it says, right? When it comes to electron gain energy, right? What you should know, with the first electron gains, right? There are 3 guys with positive electron gains, right? What are those? Only beryllium, magnesium, and nitrogen is with positive, or one can say endothermic, right, values, and all other elements are with negative exothermic values. That is about the first electron gain. About the second electron gain, what we know, all elements are with positive endothermic values. This is the simplest idea, right? This is because existence of the stable electron configurations, right? The reason here is, right, existence of stable configurations. They refuse to gain an electron, so those are endothermic values, right? Energy should be supplied to give an electron to these guys, right? Okay, these two are with S2 configurations. This is with NS2 NP3, right? The subshell is exactly half filled. It's a stable situation, right? Okay, so that is the idea. So electron gain energy of beryllium is positive. So the statement is true. The statement is true, right? That is about the second statement, right? Let's move to the third statement. Statement 3. The spacing between two adjacent lines in a given series of atomic spectrum of hydrogen decreases gradually in the direction of decreasing wavelength, right? So this is about the hydrogen spectrum, right? Hydrogen spectrum. What we know about the hydrogen spectrum, right? So this is all about the direction of decreasing wavelengths, right? The spacing between two adjacent lines in a given series of atomic spectrum of hydrogen decreases gradually in the direction of decreasing wavelength. So if you take a series of lines, right? Let's take the Lyman series. If you take a series of lines, what will happen? Going towards the higher energy region, the spectral lines become closer to each other, right? Like this, no? Spectral lines become closer to each other, right? This would be the first line of the Lyman series, second, third, fourth, fifth, sixth, like that. So going towards higher energy region, spectral lines become closer to each other. Higher energy means, right? higher energy means, as these two guys are constants, higher energy means lower frequency, right? Greater than energy means lower your frequencies. So going towards higher energy regions, that means going towards lower frequency regions, right? The spectral lines become closer. Right, one can say, right? Energy increases means, right? That means lambda decreases toward this side. Toward this side, lambda decreases. Right? Energy increases means going towards here, lambda decreases. That means going towards this side, lambda increases. Opposite relationship between the two, energy and the lambda, right? So let's go to the statement again. The spacing between the two adjacent lines in a given series of atomic spectrum decreases gradually in the direction of decreasing wavelength. Direction of decreasing wavelength is this. So spaces between the spectral lines decrease. Okay, this is the increasing direction. If you need to copy the decreasing direction, this is the decreasing direction. Age increases means wavelength decreases, right? Okay, so the statement is true, right? No? Right. Let's copy the fourth question, the fourth statement. Statement number 4. The de Broglie wavelength associated with the N2 molecule is shorter than the de Broglie wavelength of O2 molecule when traveling at the same velocity. Right? Let's see. De Broglie wavelength. De Broglie wavelength. What is the equation for that? So lambda is equal to, right, h over p. P is the momentum. De Broglie wavelength is equal to Planck constant divided by the momentum. Momentum is mv, mass of the particle into its velocity. Right? This is the de Broglie's equation, and it says with the N2 we have to now compare the N2 and the O2 molecules traveling with the same velocity. Traveling with the same velocity. Right? This is a constant, Planck constant. Traveling with the same velocity means this is also going to be a constant for this question. Right? Same velocity. This is a data. So it's also a constant, right? So this equation simplifies to what? Lambda is proportional to 1 over m. Right? With the look of that, looking at that, we can now discuss, right? N2 molecule is shorter than the difference of O2 molecule. So N2 and O2, right? So when it comes mass, right? N2 is lighter and O2 is heavier. O2 is your 8th atom, 8 and 8, 16. Molecular weight is 16, right? Sorry, one oxygen carries 16, so molecular weight is 32 G mole minus 1. For this one is 28 per mole, right? Per molecule, it is going to be divided by the Avogadro's number, weight of a molecule, right? So mass varies like this. So the lambda variation should be the other side, right? Because when the mass increases, lambda decreases. Inverse relationship. So it goes to lambda of N2 is going to be greater than lambda of O2, right? Okay, let's see what it says. De Broglie wavelength associated with the N2 molecule is shorter than that of O2. That is what they are saying. No, de Broglie wavelength of N2 is greater than that of O2. So the statement is false. Statement is false. False statement. Right? That is about the statement number 4. Let's move to the statement number 5. Statement number 5. See, the effective nuclear charge felt by a valence electron of carbon is greater than the effective charge felt by a valence electron of phosphorus. That is a statement, right? See, this is about the effective nuclear charge. Nuclear charge. So, see what we know about that thing. So, when it comes to effective nuclear charge, right? What we know. So, what are the trends we know? Going towards right of a period, going towards right of a period, going towards right of a period, what we know, your effective charge increases, right? We can denote it as, is it effective, is it EFF increases, right? That is why your atomic radius becomes smaller going towards right of a period, right? Effective charge is the charge actually the charge felt by a electron is referred to as the unity charge. The nuclear charge felt by a electron is referred to as the unity charge. It increases going towards right as your number of protons in your nucleus increases, right? So going towards right, the unity charge increases, right? Going towards down, what we should know? Going down a group, going down the group, what we know? So going down a group, what we know is your effective charge won't change that much, remains the same. Remains the same. That is what we should know, right? Okay, so let's come up with the question now. So the effective charge felt by a valence electron in carbon is greater than the effective charge felt by a phosphorus. See, we are looking for carbon and phosphorus, right? So in your period table, if you think of your period table, so I'm going with P block, right? You would see boron, carbon, nitrogen, oxygen, fluorine, neon. That is your second row. You take the third row of the P block, right? Aluminium, silicon, phosphorus, sulfur, fluorine, and argon. So we are supposed to compare these two guys. Compare these two guys, right? So going towards right, the differential charge increases. So the differential charge of nitrogen is greater than that of carbon. The differential charge of nitrogen is greater than that of carbon, and the nitrogen's differential charge is same as the phosphorus, going down as it is remaining same. Right? That is how we are supposed to come up with the answer, right? So is a DFF of nitrogen is greater than of carbon because of this trend going towards right, if charge increases, but the phosphorus value is equal to the nitrogen's because going down the value is not changing, right? So that we can say if the charge of carbon is actually smaller than the charge of phosphorus, right? So what is the statement again? Filled by valence electron of carbon is greater than. They are saying carbon is greater. No, it is false. Carbon is smaller. Statement is false. Right now, it is about the statement number 5. Right. Let's discuss about the statement 6. See what it says. Statement 6. Right. All CO bonds in carbonic acid H2CO3 are equal in length. Right. That is what it says. Right. All CO bonds in carbonic acid are equal in length. Right. So carbonic acid H2CO3. Right. So the structure is going to be like this for the carbonic acid, right? The Lewis structure is like this, right? This is the carbonic acid Lewis structure, H2CO3, right? H2CO3. So this guy won't come up with an hybrid, right? This guy won't come up with a hybrid, right? Because this is the only stable Lewis structure we can draw for the H2CO3, right? This is the only stable Lewis structure for H2CO3. That means no resonance hybrid considerations, right? And what we know is, right, bond length is depending on bond order. Bond length is depending on bond order. And bond order when bond order is high, your bond length is low. That is the theory we are using here, right? When bond order is high, bond length is more. The number of, if you are with more number of bonds between your atoms, your bond length is more, right? So you can clearly see as the bond order varies with these three guys, right? Basically with these two, the bond order varies. With these two also bond order varies. So bond order varies means bond lengths also should vary. Bond lengths also should vary. If you have to mark these bonds as A, B, and C, right? As these bonds, the A and B bonds are with same number of bonds. These two species are with the same number of bonds. We can say the bond order of the bond A and B are equal, but with bond C, you are with greater bond order, right? So there are two bonds there between the carbon and oxygen. Here, only one bond, right? Bond order varies like this. That means bond length, because bond length, the A and B bonds are with equal lengths, but the C bond should be smaller than the A and B, right? Because when the bond order is high, bond length is small, right? So the statement, when it comes to statement, all CO bonds in carbonic acid are equal in length. So that is false. C is smaller than the bonds A and B here. So the statement is false. Right now, that is about the statement 6 here, right? Let's come up with the statement 7. Melting point of I2 is greater than that of H2O. Melting point of I2 is greater than that of H2O. That is what it says. So this is about melting points of covalent compounds, right? So melting points of covalent compounds depends on two things, right? What are those? The molecular weight and the strength of secondary interactions, right? That is the idea. So how to come up with a good answer here? It's like this, right? So when molecular weight difference, in the molecular weight difference, delta MB, delta NW, molecular weight difference is greater than 50 units, normally when greater than 50 units, what we are saying is, right, the compound with the greater molecular weight will have the greater melting point, right? Compound with higher molecular weight is with greater melting point, right? So the second thing is considered when the molecular weight difference of the two considering species are less than 50 units. Then we can say, right, we have to look for the right strength of second interactions, right? So we can say when second interactions are high, the second interaction strength is high, that species is with a greater melting point. That is the idea. So when we are considering the I2 and H2O, when you are considering the I2 and H2O, that comes under this category, right? Why is that? When it comes to I2, its molecular weight is what? One I didn't carry 127, so I2 is 254 G mole minus 1. When it comes to H2O, its molecular weight is 18 G mole minus 1. So I2 is very heavy. So it is very hard to do the thermal motions with the I2. It is very hard to do the thermal motions with I2 because to melt a substance, to convert the solid into a liquid, you have to move the particles, right? You have to move the particles, right? So that is hard with the I2 as it is heavier. So hard to do the thermal motions here. So hard to liquidize the I2. So that you can see in this reason, right? Compound with higher molecular weight is with higher melting point, right? So if you think of right molecular weights, think of molecular weight, I2's molecular weight is greater than 50 units compared to the H2O. So melting points, because the melting point I2 is with a greater melting point than water, right? The melting point of I2 is actually 58, which is a solid at room temperature. I2 behaves as solid at room temperature. Do not melt with the temperature of the room conditions. But H2O appears as a liquid. That means melting point is achieved with the room temperature, right? So H2O behaves as a liquid at room conditions, but I2 is a solid. Didn't achieve the melting point at room temperature, right? So I2's melting point is greater than that of H2O. So that is the practical situation. Let's go to the statement again. It says melting point of I2 is greater than that of H2O. Yes, the statement is true. That is true. So we can say the statement is true. Statement is true, right? That is about the right statement 7. Let's do the question number 8, right? This is the question number 8, right? Statement 8, right? It says length of London forces in pentane is less than that of 2,2-dimethyl propane, right? So strength of London forces in pentane is lesser than that of 2,2-dimethyl propane, right? That is what it says, right? So pentane and 2,2-dimethyl propane, right? London force strength. Okay, London force strength. So strength of London forces depends on two factors, right? What are the two factors? The molecular weight. When molecular weight is high, right? When the molecular weight is high, right? London strength is high. What is the other thing? When molecular weights are the same, or one can say closely related, we look for the effective surface area, or the contact points. Effective surface area. When it is high, London strength is high. Right? Okay. This can be referred to as the number of contact points. Right? So let's discuss about the two guys. One is pentane, the other one is 2,2-dimethyl propane. So pentane is this kind of a molecule. Pentane, this 5-carbon molecule, right? This is your pentane. Right? It is referred to as the C5H12, that is the molecular formula for the pentane. 2,2-dimethyl propane. Right? It is also with the same molecular formula, right? C5H12. But how it appears is like this. 2,2-dimethyl propane is like this. This is the structure of the 2,2-dimethyl propane, right? Okay. So if you are to compare these two guys about the London bond strength, London force strength, right? Both are the same molecular weight. Both are the same molecular weight. So what we need to consider is actually the effective surface area. The one with the greatest effective surface area should have the greatest London force strength, right? So when it comes to effective surface area, this guy's effective surface area is this, right? The surface area of pentane, no? The surface area of pentane, right? So all the surface area is referred to as the effective surface area for the pentane, right? All can be referred to as an effective surface area for the pentane. But when it comes to 2,2-dimethyl propane, even though the surface area looks like this, right? Its effective surface area is just these areas, this thing and this thing. This section, no? Only those can interact with other molecules to form London instructions, right? So we can clearly see the effective surface area of this thing is greater than the effective surface area of 2,2-dimethyl propane, right? This is only the effective surface area, but here with this guy, all the surface area can be considered as kind of a effective surface area, as all that surface area can be used to form London interactions with other molecules, right? That is the idea. In this case, only these spaces can be used to form London interactions with other molecules, right? So effective surface area of pentane is greater than that of dimethylpropane, so that pentane should have a greater London force strength than the 2,2-dimethylpropane, right? So you can say London strength of pentane should be high than the London strength of 2,2-dimethylpropane, right? Yes, discuss the statement again. Strength of London force in pentane is lesser than that of 2,2-dimethylpropane. Lesser than. That means the statement is false. Pentane is with a greater London force strength than the 2,2-dimethylpropane, right? So we have to consider the each statement as a false statement, right? No, that is the review for the statement 8. Let's review the statement number 9. Ionization energy of argon is greater than that of oxygen. Ionization energy of argon is greater than that of oxygen. That is what it says, right? So this is about the ionization energy. The first ionization energy, let's take it like the first ionization energy, I1. So when considering first ionization energy, right, we have some considerations, right? What are the things you should know about the first ionization energies, right? So first you should know the I1 minimums and I1 maximums. So let's discuss about those things. The maximum values of I1 is with noble gases. Those are the ones which are not keen to release electrons, right? Noble gases. So the greatest I1 is with the smallest noble gas, helium, then neon, then argon. But we have a VIP gas, it is fluorine, right? All the other 20 elements, first 20 elements are with less values. When considering first 20 elements, right? When considering first 20 elements, we are writing this, right? So when it comes to I1 minimum values, the ones which are more keen to release electrons, those comes with group 1 elements, right? There we can say the largest group 1 is with the minimum value, that is suppose I had potassium out of first 20 elements we are discussing here. So sodium is bit smaller you are hard to release electrons, right? So lithium, all the other guys are with greater values than these ones. Group 1s are very keen to release electrons, right? So let's say it will be sufficient to release the electron. So ionization means that no, the minimum energy needed to release an electron from your gaseous state, no, gaseous element, no, to produce the gaseous ion, right? Okay. So these are the things we should know. Then we should know about the zigzag along the period. Zigzag along the period, right? So period trend, right? That would look like this, right? With the first line, you have the corners, right? With the second longer line, you have the corners as well as the center. The third longer line, again, corners as well as the center, right? So that is how the 8 elements appear along the period, right? So group 1 guy is with the smallest value again using CLC, and group 18 is with the largest, right? So this is second group, third group, sorry, group 13, group 14, group 15, group 16, and group 17, right? Okay, actually with the use of this thing and yeah, with the use of this, we can come up with the answer, right? So I just trying to remind you the theoretical points you should know here, right? Ultimately, you should know about the diagonal relationship as well. Diagonal related atoms are with diagonal related atoms are with some similar kind of relating values for the first ionization, right? So basically, when it comes to diagonal relationship, is applied for p block, right? Third and second and third periods, right? So these are the guys, no? Right? So we consider diagonal relationship between these guys, these two, and here, right? These are the ones with the diagonal relationship, not this, right? This is with a fairly high the difference between the values, right? As nitrogen is become coming up with somewhat stable configuration, right? So these guys can be related, right? These guys are with somewhat close to similar values, right? Somewhat close to similar values, right? But remember, the group 2 guy is with bit of a second row guy is with a bit of a larger value than the first row guy. Sorry, third row guy. We had discussed about that, right? Second row guy is with a little slightly higher value than the third row, right? Okay, that should be also known. Finally, what you should know is the position of hydrogen. Position of hydrogen. So basically, where the hydrogen appears. So hydrogen is in between, what? In between nitrogen and oxygen, NO. In between nitrogen and oxygen, the hydrogen appears. Right? The position of hydrogen is also should be known. Right? These are the all the things we should know about the first electron, first ionization energy. Sorry, first ionization energy. Right? So let's come up with the answer. The answer is very clear. Ionization energy of argon is greater than that of oxygen. Yes, argon comes with a maximum value as it's a normal gas. Right? So the statement is true. Statement is true. Right? Simple answer. Right. That is all about the statement 9. No, statement 9. Right. Now the statement number 10. Right. Let's copy the statement number 10. Right. The lowest melting point of 3D elements is with zinc. The lowest melting point of 3D elements is with zinc. See what it says. Right. This is about the melting points of metals. Right. So in 3D elements, when consider 3D elements, right, all are metals. All are metals, right? So we have to discuss about the melting points of metals here, right? Melting points of metals. This is the consideration here, as all the 3D elements are metals, right? Okay. So when it comes to melting points of metals, that depends on the metallic bonding strength. It depends on the metallic bonding strength, right? When metallic bonding strength is high, your melting point is high. right? That is a theory we are going to use here, right? Towards metallic bonding strength, three factors affect. Three factors affect. The first thing, number of electrons released to electron C, right? When it is high, metallic bonding strength high, metallic bonding strength high, that means your melting point is high, right? Second thing, second thing, right? The size of the radius of metal cation, right? So when it is low, you have a greater charge density with the metal cations, so those will attract heavily towards the electron Z, right? So when the size of the radius, when the size of the radius of the metal cation is low, that means your metal charge density of the metal cation is high. That means your metallic bonding strength is high, so that the melting points of your metal becomes high. The third factor, and these two are closely similar, the third factor comes to play, right? The third factor is ionic nature. So the D block things, this is very important. It's not used in S block situations. Not considered when comparing S block elements, but needed to compare the melting points or the melting bonding strength in D block guys, right? So it says, but in ionization energy, in the ionization energy, right, is low, when the ionization energy is low, you can release more electrons easily, so that your metallic bonding strength will be high, right? That means your melting points will be high. So opposite is true for lower melting points, right? When the ionization energy is low, melting point is high. When the ionization energy is high, the melting point is low. Some inverse relationship with the ionization energy, right? So that is what matters with the sink. That is what matters with the sink, right? What happens to the sink? In considering sink, that sink is with argon configuration with 4s2 3d10. So it's a stable configuration. It's a stable configuration. So zinc is not keen to release electron to electron C. So the ionization energy of the zinc is high, right? So not keen to release electrons to the C. So its ionization energy is high. That means its melting point is low. The lowest melting point of 3D elements coming up with zinc, as it is with a stable electron configuration, so that the ionization energy will be high, so that the melting point will be low, right? As those guys are not keen to release electrons to electron C, right? So the statement is true. So the statement is true here. Let's discuss about the statement number 11. See, both BCl3 and carbonate are with same shape and both are non-polar, right? So we are referring to BCl3 and carbonate. See how those two things are appearing, right? BCl3 and the carbonate, right? BCl3. It will be like this, right? I have drawn the Lewis structure with this shape, right? The carbonate, right? So it appears as a resonance hybrid in nature, right? So it will be looks like this, right? This is a resonance hybrid of carbonate, right? Okay. So let's go to the things. Same shape and both are non-pole. Yes, both are the same shape. What is the shape? Shape here is trigonal plane, right? And this one is also with the shape, right? And the polarity, both the same shape. What about the polarity? So if you have to mark the polarity, right? First you need to come up with the dipole moments, right? If the dipole moments cancel off, if the net dipole moment is zero, such a species is referred to as a non-polar species. If the net dipole moment is not equal to zero, those are referred to as polar species, right? That is how we are supposed to come up with the polarity of the species, no? Right? So if you are thinking of this, right, dipole moments appear like this, going towards chlorine, the arrow hits, right, as chlorines are more treated than the boron, right? So the net dipole moment will cancel off, right? All of these three things are with same values as they are individual dipole moments. So as dipole moment is going to be a vector, it will cancel off, right? So net dipole moment is zero. Net dipole moment is zero. So this is a non-polar, non-polar molecule. When it comes to this one, so this guy also, we are with a zero net dipole moment, bro. We need to consider the existing structure in nature, right? So all the three bonds, the dipole moments of the three bonds will cancel off like this. So it is also with a net dipole moment zero. So it's also a non-polar species. So both the BCl3 and carbonate are non-polar, and their shape is actually trigonal plane, right? So both BCl3 and carbonate are with same shape and both are non-polar. The statement is true. So the statement is true. We can take this statement as a true statement. That is the review for the statement 11. Right. Let's come up with the statement 12. To calculate the percentage ionic character of a covalent bond, both the dipole moment and the bond length data are needed. Right? Both the dipole moment and the bond length data are needed. That is what it says, right? So how to calculate the percentage ionic character? What is the equation there? So you think of the equation of percentage ionic character, right? The equation is the actual charge, that means the delta charge appearing with one atom, with considering atoms, divided by the charge if the bond is 100% or completely ionic. Charge of atom on atom if the bond is 100% ionic into 100%. So this is the formula we use to come up with the percentage ionic character. Right? Okay. So it's like this, no? If you have to consider HCl, to take the example, HCl. So you know this bond is polar. This bond is polar. So this guy's unit is 2.1. This guy is 3.1. So this bond is polar. So that you have a negative delta here. So delta here appearing, right? So this is the actual charge appearing on this atom, right? So actually, to calculate this actual charge, how this is calculated? Calculate the actual charge. Actually, we need to use the equation of dipole moment. Use the following equation. What is that? Your mu dipole moment is equal to delta R, right? So mu means dipole moment of the bond, and R means bond distance between two atoms, right? So these are the practical data we obtain, and using those only we are able to calculate the delta, the actual charge on atom, right? That is used to come up with the percentage ionic character. So the statement to calculate the percentage ionic character of a covalent bond, both the dipole moment and the bond length data are needed. That statement is actually had to be taken as a true statement. To calculate the percentage ionic character, we need the delta. To calculate the delta, we need the dipole moment and the bond distance. Those data, those are the practical data. Bond distance or bond length, both are same, right? That is about the question number 12, the statement 12, right? Let's discuss about the statement 13, right? Cathode rays show a deflection in an electric field towards positive charge, while does not show any deflection in a magnetic field, right? What we can say about that thing? Cathode rays show a deflection in electric field towards positive charge, while it does not show any deflection in magnetic field, right? So when we are discussing about cathode rays are negatively charged. Those are the electrons naturally, right? So when it comes to negatively charged particles, those should do some deviations in electric fields as well as magnetic fields. Deviation means should change their direction of movement, right? Okay. So what are the observations? Those will deviate in an electric field towards the positive terminal, the opposite charge terminal, towards the positive plate, right? When we are considering about a deviation of the magnetic field, how it comes. So in a magnetic field, deviate in an in a magnetic field actually not towards any of the poles but perpendicular to the field, right? Not towards any of the poles but perpendicular to the field. Perpendicular to the field, to the magnetic field. Right? That is what we should know. So, in your statement number 13, they are saying does not show any deflection in a magnetic field. Such a statement is there. So, that is false. Right? In a magnetic field, right, they deviate perpendicular. Right? Deviate perpendicular to the magnetic field. So, this your statement is false. As they are saying, right, no deviation there. The statement is false. Statement is false, right? No? Okay, so that is about the statement 13. Let's discuss about the statement 14. EOM ratio of a proton is greater than that of an electron. See what it says is about the EOM ratio. EOM ratio. That means what? EOM ratio means charge to mass ratio, right? This ratio, right? Let's consider that we are supposed to compare between the proton and the electron. Proton and the electron, right? In proton, right? Its relative charge. Relative charge is +1, right? Let's take the mass as mp. For electron, you know, the relative charge is -1, and let's take the mass as me, mass of an electron, and we know that mp is way greater than me, right? What we know is mp is actually 1837 times of me, right? That means mass of proton is very greater than the mass of electron. This known stuff, right? Okay, let's use this knowledge to come up with the EOM ratios, right? So, if you take the EOM ratio for proton, it looks like just 1 over mp, right? So, if you think of EOM ratio of electron, it is looks like 1 over me, the mass. So, as the mass here is greater and mass here is smaller, the EOM ratio here is greater and here is smaller. Right? That is the idea. So let's go to the statement again. EOM ratio of proton is greater than that of electron. EOM ratio of proton is actually lesser than that of electron. So EOM ratio is right greater with the electron, not with the proton, right? So EOM ratio for the proton is smaller and the electron is greater, right? So the statement is false. So the statement is false. False statement, right? No, that is the review for the statement 40. Let's discuss about the question number 15. So there we are supposed to write the answers to the questions given below on the dotted lines, right? Okay, see. Of the three ions Na plus, magnitude plus, and F minus, which one has the smallest radius, right? So we are referring to ionic radius concepts, right? The three guys given now, Na plus, Mg2 plus, and the F minus, right? Actually, all those things are with 10 electrons each, right? All the guys are with 10 electrons each. Sodium is your 11th atom, Na plus means 1 electron is removed, only 10 electrons here. Magnesium is your 12th atom, 2 plus means 2 electrons are removed, that means 10 electrons here. So F minus is your 9th atom, 1 electron is gained, that means 10 electrons are there. So all are with 10 electrons. So these are can be referred to as isoelectronic species. What we should know about the isoelectronic species? When it comes to isoelectronic species, what we know is when charge of the species is high or the positive nature is high, charge means I'll write it like this, when positive charge of the isoelectronic species is high, their radius, the size is small. It is the theory applying in the isoelectronic species, right? So radius of the size is small. So the ionic radius is then going to be this is kind of a inverse relationship, right? The one with the greatest charge should have the smallest radius. So the magnesium is with the smallest radius. The one with the greatest charge is with smallest radius, and with the one with the smallest charge should be with the greatest radius. Things are like this. So they are looking for the smallest ionic radius. So smallest thing appears here. So smallest radius coming up with magnesium 2 plus. So answer is magnesium 2 plus for the question number 15. Right, let's come up with the question number 16. Of three elements CNO, which has the highest second ionization, right? This is regarding the second ionization energy. Second ionization energy, right? They have given carbon, nitrogen, and oxygen, right? What we should know about second ionization energies? These are regarding the same raw elements for the second ionization, right? So we have to come up with the zigzag here. Just draw the zigzag. In the first line, only the corners, the second and third long lines, corners as well as the center is with the elements, right? Corners as well as center with elements, right? Okay. So it comes second ionization. It comes second ionization, right? Group 2 guy is with the lowest value. Group 2 element with I2 minimum value, right? The lowest value, right? So what should be that? This is regarding the second row of elements. Second row elements, right? So the group 2 guy is what? That is beryllium. So you have to start with beryllium here. Group 2 guy, beryllium, boron, carbon, nitrogen, oxygen. Then you have the fluorine and the neon. Right? So the group 1 guys goes here. So group 1, which is in the greatest value, right? That is here with the lithium. Right? So this is the question. So they are looking for what? The greatest or smallest? Highest second ionization energy. Highest second ionization energy out of these three guys, right? So which one is with the highest synchronization energy? That is the oxygen, right? Oxygen. Out of the three, oxygen is with the greatest synchronization energy. Out of carbon, nitrogen, and oxygen, oxygen is with highest I2. So the answer is oxygen. The answer is oxygen. Right now, that is a review for the question number 16. Let's discuss the question number 17. Out of the three compounds H2O, HOCl, and OF2, which one has the most electronegative atom? Electronegative oxygen atom, right? So it's about the electronegativity. Electronegativity. Right? We have to consider three guys, no? H2O, HOCl, and OF2. H2O, HOCl, and OF2. Right? H2O, HOCl, and OF2. Right? First draw the structures. That is important. Right? Degree of oxygen here, no? Right? First draw the structures. This structure is enough. This OF2, right? Okay. So what is the first consideration? The first consideration is hybridization. First consideration is hybridization. If the S character of the hybridization is greater, your utility is high, right? See? Consider the hybridization. Right? That means its character. Right? So this one is it. 1, 2, 3, 4. Summation of lone pairs and sigmoids are 4. That means sp3. 1 is and 3 bits. Here 1, 2, 3, 4, sp3. Here also 1, 2, 3, 4, sp3 hybridization with these oxygens. So hybridization of this character is same with all the guys. sp3. So with the use of hybridization, we can't comment which one is it. They are asking the most theorem. No? So then we have to consider charge on the atom. Charge on oxygen. In all the three situations, charge is equal to 0. Is same. Equal to 0. Third thing we have to consider is the oxidation state. Oxidation state. Of oxygen here. Our concentrator means oxygen. So what is the oxidation state? Let's come up with the oxidation state. So these two electrons are actually approaching towards oxygen. So oxygen is a positive, hydrogen is negative. Oxygen is a positive and hydrogen is negative. So the oxidation state of oxygen is going to be then +2. The oxidation state of oxygen is going to be sorry for that line. As these electrons are approaching towards oxygen, oxygen is a negative, hydrogen is a positive. Right? Oxygen is a negative, hydrogen is a positive. That means around oxygen, you are with -2 charge. Oxygen state is that, no? Charge on your considering atom when all the bonds are considered to be ionic. If these bonds are ionic, oxygen is a negative charge and hydrogen is a positive charge, as oxygen is more electric than hydrogen, right? So with these ones, oxygen is a negative, hydrogen is a positive, negative, positive. So the charge on the oxygen is again -2. For this, as fluorine is more electric than oxygen, fluorine is a negative, oxygen is a positive. Positive for the oxygen. So oxygen state of oxygen here is +2. Right? So in the oxygen state, you can write the H2O and the HOCl are with same oxygen states, at the -2, but the oxygen state is greater in oxygen of OF2. So as the oxygen state is high with the OF2, its electronegity is high. They are looking for the highest electronegity. Yeah. So the electronegity of oxygen. So electronegity of oxygen is actually greater in OF2 compared to these two guys. We don't need to compare about these two, right? If you are thinking of OF2, it is with the greatest value. The OF2 is with the greatest oxygen state, that is actually greater than H2O's and OF2's value. Sorry, HOC's value. Right? I just went with the answer, right? They are looking for the greatest value, so that is OF2. If you need to compare these two guys, you have to come up with the right next form as well. That is the situation of surrounded atoms. In the situation of surrounded atoms, if more electronegative atoms are connected with you, your electronegity also increases, right? So with that, you can say out of these two guys, the electronegity of this guy is greater than this, right? If this guy is HOCl is greater than H2O. That comparison can be done with the use of the fourth point, which is actually the electronegity of connected atoms. But anyway, for this question, they are looking for the greatest electronegative species, right? The species with the greatest electronegative oxygen, that is actually OF2, right? So the answer is OF2. That is the answer of the question number 17, right? Okay. Let's discuss the question number 18. What it says: of the three elements, beryllium, carbon, and nitrogen, which one will liberate energy when an electron is added to its atom? That thing, right? Okay. So this is all about electron gain, no? When an electron is added to gaseous atom, the energy release, no? Energy release or energy change occurs is considered as actually electron gain energy, no? Electron gain energy. Electron gain energy. Right? So what is the question? So what we know is when considering first electron gain, right? Beryllium, magnesium, nitrogen are with endothermic values. Endothermic means positive values. That means endothermic means what? Endothermic means energy absorbs, not releases. All others are with exothermic, right? Values. Exothermic means exothermic means energy releases there. when absorbing an electron, energy is released. So the three atoms we are concerning here is beryllium, carbon, and nitrogen. Beryllium, carbon, and nitrogen. So beryllium, nitrogen appears here. So carbon appears here. So carbon appears here. All other atoms. So carbon is the exothermic first electron gain. That means carbon releases energy when gaining an electron, but not the beryllium and nitrogen. But not the beryllium and nitrogen, right? So of three elements, they are asking us to come up with the atom with which liberate energy, which releases energy. It releases, energy liberates, releases, right? So that situation is appearing only with the carbon, not with beryllium and nitrogen. So the answer is carbon. Out of beryllium, nitrogen, and carbon, carbon is the only one which releases electron. Sorry, which releases energy. Which releases energy when attracting an electron, when gaining an electron, right? So answer is carbon. That is the review for the question number 18, right? Let's discuss about the question number 19. Of the three ionic compounds NaF, KF, and KBr, which one has the highest solubility in water? Highest solubility in water, right? This is about solubility of ionic compounds in water, right? Right? Solubility of ionic compounds in water, right? Solubility of ionic compounds in water depends on two things. Depends on two things, right? Depends on two things, right? Depends on two factors, right? One is the strength of ionic character. One can say the ionic character, right? Greater the ionic character, greater will be the dissolution. When ionic character is high, solubility is high. That can be written. So basically, we say ionic compounds easily dissolve in water. Ionic compounds prefer polar regions like water to dissolve, right? So the second, there is another thing actually which will be learned with the unit 5 energetics, right? That is referred to as lattice energy, and hydration energy, right? Those are two considerations, right? But for a question like this, in the in our paper question number 1, basically regarding the general chemistry, right? We are looking at this, right? This will be learned, right, with the unit 5, right? This is what appearing in the unit 1 and 2. Let's come up with the answer with the use of this knowledge. When the ionic character is high, solubility is high, right? Okay. So ionic character depends on porosity power and the porosity of the cations and the anions, right? So we can say when the cation is with a greater Q plus, and with a small r minus, its polarizing power will be high. Or when you are with an anion with sorry, large charge and with a larger radius, then their polarizability is high. When this happens, right, your covalent character increases, the ionic character decreases. Covalent character increases and ionic character decreases. So that your solubility in water solubility will decrease with these effects. Right? Okay, that is what you should know. Let's compare the stuff, right? NaF, KF, and KBr. Let's compare. NaF, sorry, NaF. KF and KBr. KF and KBr. I write it here. Br is larger compared to the other two anions, right? So they are looking for the one with highest solubility. Highest solubility means the opposite of this rule. Opposite of the rule, right? Highest solubility means opposite of these things should happen. Opposite of these things should happen for the highest solubility. Let's look for the highest solubility. For the highest solubility, Q plus should be low, R minus should be high, Q minus should be low, and R minus should be low, right? For the highest solubility, right? We are looking for larger radius, sorry, smaller radius. For highest solubility, we are looking for smaller radius. So this is out, this is out. With the anion, we are looking for smaller radius. So out of these two, we have to select. With the cation, here, with the cation, it is better to have a, so it is R plus, right? With the cation, it is better to have a larger radius to come up with the highest solubility. Larger radius to come up with the highest solubility. So out of these, this should be the answer. This should be the answer, right? Larger radius, right? This is smaller, so larger radius. So answer is KF. Answer is KF. So answer is KF. KF is the one with the highest solubility. Highest solubility. Right now, that is the Q for the question number 19. Let's discuss the question number 20. Of the three compounds HCHO, CH3F, and H2O, which one has the strongest intermolecular forces? Strongest intermolecular forces, right? So this is about strength of intermolecular forces. That means intermolecular force means second interactions, no? What we know is actually, right, because second interactions, ion dipole is in the greatest strength, then hydrogen bonds, then the other dipole interactions other than the hydrogen bonds, right? And ultimately the London forces, no? That is how the strength of second interactions vary. Let's see the guys appearing here with the question. HCHO, HCHO, that is this, and what else? CH3F, CH3F, and H2O2. H2 is a compound like this. H2O2. See, so this is a polar molecule. You see, this is a polar molecule. So there is a polarity, right? These electrons are attracting towards carbons, right? And these are attracting towards oxygens. So there is a net dipole moment, right? Ultimately, right, towards here, net dipole moment is there, right? Mu is not equal to 0, so it is a polar molecule. So dipole level interactions appear, and you won't see the formation of hydrogen bonds here because you don't have a hydrogen connected to a more CH2 atoms. The hydrogens are not connected to more CH2 atoms, so you don't see the formation of hydrogen bonds. So this is just dipole interactions. What about this? So this is also a polar compound. See, the electrons are attracted towards the carbons with the CH bonds, and the electrons are going towards the fluorine, the CF bond. So you have a dipole moment like this in this case, right? So the net dipole moment is not equal to 0. It's a polar molecule. See whether hydrogen bonds can be formed here or not. No, you can't form hydrogen bonds because hydrogens are not attached to a more electron atom. So just dipole appears there. What about this one? So you clearly see, right? These forms, no? OH polarity, right? So with these, you can think of formation of hydrogen bonds, right? So OH groups appear. So definitely hydrogen bonds are there. So they are looking for the greatest or strongest intermolecular interactions. So out of dipole and the hydrogen bonds, these guys are with the strongest secondary interactions. So your answer is H2O2. H2O2. Right now, that is the answer for the question number 20. Right? So that's all for the discussion today. So let's meet with the next discussion next week. Goodbye then.